So, what I'm not going to do is to tell you anything medical. This is about one of my hobbies, which is clocks and clock collecting. Again, I've got no special messages, no expertise medically to pass on, so I thought I'd do something that I did know a little bit about. Forgive me if you don't have any interest in clocks at all. Could I just have a show of hands? Is there anyone who's not wearing a watch of some sort tonight? Well, I'm astonished. How do you know what time it is to get here? Stephen Fowley, our medical director, you were slightly late. That's because you haven't got a watch. I'm sure that the trust provides one. Okay. So, hold your ears. Astonishing. 355 kilograms, banging that bell umpteen times a day. Now, this is my wife. I'm photogenic, and this is just to thank her for putting up with me organising this talk to take a very long time, including quite a bit of our holiday in Tunisia a couple of weeks ago, and also for hosting the President's meals at our house after each lecture. So thank you very much, Pat. Not a year over 60. This is another lady who's also really important in my life. This is Julie D, who is our urology theatre manager, and she really controls what we do, I can tell you. What she's pointing at is that by list, I've actually started at 8:15. This is a quarter of an hour before the list should actually start. That's good. What we will do is to visit Julie at 2 other times during this presentation. Now, for a long time, man has known that half of the day is sunlit and half of the day is dark. So here you've got dawn, and the sun always rises in one side of the world and then sets in the other. So, as I said, this was very obvious to cavemen, for example. In particular, also cave women. They also knew that the stars rose in the east and set in the west. They also knew that the stars had a very fixed pattern, interestingly, and some of them you could make in the shapes possibly of animals, which is now what we call constellations. They also knew that the Earth seemed to weave a path through the stars, and that is called the zodiac. They also knew, a long, long time ago, that within that zodiacal path there were what were called vagabond stars. Those are stars that don't move in conjunction with the others. They move all over the place, and those are the planets. So all of that was known. They also, of course, knew, as it's glaringly obvious, that the moon starts off small, gets bigger, and then gets small again. And that happens day in, day out, and took about 28 days. They had an interesting view of the solar system, and again this goes back to ancient times. They put the Earth at the middle of it. This was, of course, wrong, as we'll find out, rather like Bulwell thinks it's the centre of Nottingham. The moon rotates around the Earth, that's true, but the other planets they had, the vagabond stars, had these very bizarre orbits. Outside all of that was the universe of stars. They also knew from a very early time that if you stuck a stick in the ground, it cast a shadow, and the length of that shadow varied throughout the day. But at one time each day, the shadow was at its shortest, and interestingly, that direction of the shortest was the same every single day. That, we know, is the meridian, which goes from north to south. They also knew, very cleverly, that there were 2 days each year when the night and the day were exactly the same length. Those are the equinoxes. They also knew that that shadow was very long on one day, the longest, and very shortest on the other, and those are the solstices. So all of that was observation. Now we're beginning to see what the use of time was beginning to be. And actually, it started off as a mixture of being interested in the universe, but also being interested in religion. And that actually a lot of the events and the gods and so on were tapered towards these astronomical events. So here we have, of course, familiar Stonehenge, and we all know that if you stand at the altar stone and look at the heel stone somewhere away, on the longest day of the year at dawn, you can see an exact straight line between the 2 posts. So they knew a lot of astronomy 3,000 years ago. Obelisks, used a lot in Egypt of course, were actually the first sundials. And again, clearly the link between time and religion has been made. Now, this isn't Egypt, this is Blickling Hall in Norfolk. Stunning Egyptian mansion. Tudor mansion where in fact Anne Boleyn was born. This is Patrick Bates. Patrick is looking worried, and Patrick is standing as what's called the gnomon of a sundial, which they put in the ground there. And he's already found out one of the problems with trying to measure time by the sun, and that is there's no sun. So there's no shadow, so you can't measure anything. But there we are, Patrick's happy because the sun has come out, and it's casting a shadow. And it's casting a shadow between number 5 and number 6 markers on the ground. And what does my watch say? 5:30. So in fact, measuring time by sun is very accurate, and became even more accurate as the precision of making sundials developed. Other things that we use, water, the leakage of water out of a vessel. So this is an Egyptian water cock, little hole at the bottom, water runs out, and you measure the level of rings on the inside, and you can tell how quickly it's emptying. And this is not so much how to measure 24 hours in a day, but it's more to time how long it takes to do things. In fact, water clocks became highly sophisticated and were used for hundreds of years. So this is a manuscript from the Bodleian Library in 1285, which shows actually a very sophisticated water clock, turning wheels and things pouring onto it. Interestingly, the day had been divided by the Babylonians into hours, 12 hours of the day and 12 hours at night. And this is something that carried on from their time right up to now. This is another way. The sand glass, used in ancient times, still used today. And here is the first illustration of sand glass in a fresco in Siena, 1337, to show it clearly being used. Again, these are more measuring periods of time rather than timekeepers. The big revolution came with the invention of mechanical clocks. Forgive me, I'm going to spend rather a lot of time on this because it's the thing I'm interested in. Clockwork, that is using wheels with teeth, probably been investigated by Archimedes. So that's about 150 BC, a long time ago. But probably the first time, at least in writing, that it was ever considered for clocks was by Robert the Englishman, whoever he was, possibly living in Bulwer, in a manuscript dated 1271. Whether he actually built a clock or not is unknown. The picture above, though, from about 1300, shows the very first types of clock, weight driven. This is another one, very similar sort of thing, but notice they are allocated to heaven. And again, the religious thing is very important. And here the function of clocks particularly was actually in the timing of religious services. And in fact, before they had dials, all these did was just bang a bell. And the Latin for bell is clocca, and this is why they're called clocks. So, what do you need for a mechanical clock? It sounds pretty simple, really. you've got to have a power source, which is either going to be weights, which is easy, springs, which is difficult. You need an escapement which lets the power out, and you need an oscillator of some sort that lets it out at a particular rate. Now, in this little video here, we can see that in action. So we've got a spring which is connected to some wheels. All these wheels have functions, minutes, hours. If you don't have an escapement, this is what happens. The spring will just undo all its energy. So here we've got an escapement. This is a lever escapement which is letting the energy out slowly, and it's connected to a balance wheel, the oscillator, which is the thing that's letting it out at a particular time. Very clever. This is the very first mechanical escapement. I filmed this up at the British Horological Institution House in Upton, where they very kindly let me have a look around. I should have been doing something at the City Hospital during work hours. Sorry. But here we can see what's called a verge escapement. So here is a wheel, a crown wheel, and the verge staff, which is rotating, stopping it, undoing. And the oscillator here is what's called a foliote. So that swings around at a regular time interval, and it's given some power by the escapement in order to do it. This is a tower clock again. I filmed this at the British Museum, which shows a foliote escapement, oscillator, connected to a verge escapement there. These are really big wheels. These clocks are all made by blacksmiths. Clockmakers per se haven't been invented. And there are the great barrels with the ropes which connect to the power source, which is weights. And then the oldest surviving mechanical clock in the world, which is the Salisbury Cathedral clock. And you'll notice that it was actually put on the ground. All clocks originally were put on the ground, because that's where clocks have always been. And so the weights, the string for the weights, come off going up into the roof. No one had twigged. In fact, it's probably better to put the clock in the roof and hang the weights underneath. So here it is, still in working order now, 1386, minor repairs. A few years after that, big clock was put in Wells Cathedral. You may have seen some of these things. With a dial. The Salisbury clock never had a dial. It was just one that struck on a bell. And this has got a dial which has got hours and groove, but it's also got these what are called automatons, which sprint around every hour. It's a bit of fun, and it must have been tricky if that happened during the vicar's sermon. Most clocks to start with were big public clocks. Rouen had one very early, Hampton Court had one very early, big clocks. Domestic clocks, little things, probably began about 1400. And these are two clocks made in Germany. These were, again, made of iron and were weight-driven. They've only got an hour hand. The technology was not enough at this stage to measure minutes. And these were highly prized and very expensive articles, to the extent that at this sort of stage, a clock probably cost someone of upper middle class, a neurologist, for example, no, a radiologist, no, a GP, probably a whole year's salary. So these were very expensive and scarce items. This is an interesting clock because it's the first clock in existence which has a spring in it. Springs were invented in about 1430. This is a clock made in Burgundy, and on the right-hand side, in the base, is a spring in its barrel, connected to a very clever device called a fusee. Now, springs give out a lot of energy when they're tightly coiled, and much less when they're lax. The fusee is a way of being able to compensate for the difference in power outputs. So, sorry, just get this to work. This clock again is in the British Museum, and the thing on the right is actually a model of it. And you can see there's been a development here in the Folliot, the oscillator, which has now become what's called a balance wheel, rather more accurate. But again, it's connected via the same verge escapement down to the weight of the spring in its driving wheels. Although this is a couple of hundred years later nearly, there was an explosion of producing clocks of great mechanical ingenuity, but also of exquisite artistry and production. So this is a table clock made in France, interestingly. You can see the fusee below the dial, but the underneath of the table clock, which I've shown on the right there, it's got this exquisite pierced work, all hidden away. And you can see there the round thing, which is the balance wheel. I put this up as you may be familiar with. This is a clock, the style of which was invented in England. It's called a lantern clock, sorry. Thinking ahead. Lantern, not so much because it looks like a lantern, but because it's made out of brass. And there was a change clearly from iron into brass. And in fact, the Latin for brass is latter. And these may well just be Latin clocks to start with. Again, weight-driven and produced for over 100 years. As I said, clocks reached the stage of being immensely complicated, including not only time telling, but also astronomical clocks as well. This is again a clock in the British Museum, and you can see here at the top of it, it's got automator again, which moves. Isn't that pretty? Isn't that nice? Halfway through a TUR. More complexity. This is obviously a boat, and I know there are people here who recognise boats. But it's an interesting automaton which was used to travel on its wheels down the centre of a feast table. It's got little guns at the side which were programmed to fire at the host and his guests. But also, there was actually a little clock in the middle there, hidden away, almost imperceptibly so. There. These were very, very complicated. And if we look here at the next slide, with the casing taken off, you can see on the top the bellows that played the tune, and below all the gearing that made the thing move and fire all those guns. This is another thing I've just put in as a novelty, and a modern reproduction, a clock that actually gets its energy from revolving down the slope. So it doesn't have a spring in it, it doesn't have a weight, but the moving down the slope actually powers the wheels and powers the wheels. So where were all these clocks produced? Burgundy, Nuremberg, Augsburg first, then England, possibly Bulwell. And interestingly, each clockmakers at this stage produced all the bits for each clock. They weren't produced clock wheels one place, springs in another, and so on. So here we can see in this clockmaker's someone who's got a furnace on for melting the metal and a mould. There's a chap doing the wheels, there's a bit of Folliot, and there's a chap who's engraving the case. And every clockmaker's was like this. This, interestingly, is Smith's clockmakers in Clerkenwell in London during the First World War. And this is absolute mechanisation of clock production. The interesting thing is that clock production, which was becoming a dwindling industry at this time, came into its own as they were used for armaments factories, all the technology, all the skill. The works forces were beginning to get organised and forming themselves into societies. Again, Germany probably had the first ones. So these were guilds, and guilds were probably good to start with because it was to look after people who were out of work and not doing so well. It was good because they wanted to make sure that people who made clocks and were trained actually did it jolly well. But inevitably there was protectionism in this, and particularly with all the European wars, there were lots of Protestants coming over to this country who at first were shunned. In fact, were in the end invited in to help with all sorts of activities, and particularly with clockmaking, where they had enormous skills. This is the charter of Charles II of the Guild of Clockmakers in London, 1632. What else is happening in parallel with development of clocks? Well, we've had a change of heart. Bulwell is no longer the centre. It's actually the centre of Nottingham that's the centre. And Copernicus, in his measurements, decided, in fact, published some work in 1543, that in fact the sun was at the middle and everything else rotated around the cube of the Earth. Copernicus was obviously a tricky chap, because this didn't quite get accepted, and it may have been a bit too crusty. And it was actually Kepler in 1600 who really made this stick, and everyone appreciated this is the way the universe works. This is Galileo. Galileo did some wonderful things. He invented the telescope to start with. He was the first person ever to see 4 of the moons rotating around Jupiter, something at a later date was postulated to be a way of telling longitude. But interestingly, he also did a lot of work on the pendulum. He knew that the pendulum swung to the left and the right equal distances. He also knew that the determinant of that swing was not the weight on the end, but the length of the pendulum. He almost certainly did devise a clock to put this into. So this was in about 1600. There's no evidence that it was actually ever made, but there's certainly some paperwork that suggested. And this is a mocked-up model of what it might have looked like. But this is the real chap. This is the chap who's probably done more for clockmaking than almost anyone apart from 2 people. Christian Huygens worked in Amsterdam, and he was like a lot of people at that time, very wealthy, very bright, astronomer, mathematician, entrepreneur, and charity worker. And what did he do? He actually put the pendulum into a clock. So he was the first person then to actually make clocks, or ask clocks to be made, where the pendulum was the oscillator. And this happened at the pivotal date of 1657. These were produced in Amsterdam, but very shrewdly, a clockmaker from London called Ahasuerus Fromentil, a Huguenot, popped over to Amsterdam and learned how to make them. In 1658, came back and started to make them in London. The first person, and he must have made a mint of money out of it. But there's no doubt these clocks were now significantly more accurate than the old balance wheel oscillator, still a verge escape. And this is one of the very original plain-looking clocks, hour only, and there's a very simple little movement, no striking. Now, this is something that took my fancy. This is a book I've got at home on early English clocks. And this is the movement from a long case clock made by Fromentil, probably 1660. You probably can't see on the right-hand side there that there's some scratching in the back of that clock. Can you make it out? Now that actually says Elmar and Co, Leamington Spa, July 1949. That's actually my dad that's done that. He's a vandal. He's defaced this clock. In fact, it was quite common for clock menders to actually scrawl on the clocks when they mended them. I challenged him with this. He denied all knowledge. Forgery, he said, as I knew. And interestingly, this is Dad's shop. Elmar, Ernest Lemberger, Mary, his wife, in Leamington Spa. And here is Dad in his shop mending something astronomical, which was from the Ashmolean Museum in Oxford. And there he is with some other clocks, and would you believe it, that's a Fromentil clock, the movement of which he's defaced. He's in heaven now, or is he? Clocks developed along a particular pathway and style, and this is a typical little table or bracket clock which developed in 1675, 1680. This is my own little clock at home. So very briefly, you're going to hear it ding a bit. here we are. It's the most agonisingly noisy ding. Ebony cased, some ornamentation, but fairly plain. This is the back of it, which is actually more ornate, the bit you can't see. So the back plate is profusely engraved with flowers, and this is made by Jonathan Lowndes, who was quite a well-known London maker. Little short pendulum, note that. And then I've taken it out of its case, so you can hear it awfully loud tick, and there is the little verge on the crown wheel ticking away. So the date of this is probably about 1680. We don't have this on very often at home. It's very noisy. A little bit more about the escapements then, developing it. We've got the verge there on the left. The next one that was invented was a thing called the anchor, because you can see the arrangement of the bit that clicks into the wheel looks like an anchor. And this was developed probably in about 1671. Now, this is a big step forward, because if you've got an anchor escapement, you don't have to have such a big swing on your pendulum, which you have to have with a verge escapement. You can therefore have a much longer pendulum. In fact, if you have a pendulum a metre long, then it ticks seconds. So immediately you can begin to have seconds recorded. And there on the other side, we've got the French simple one, which is called a pinwheel escapement. I put this in as a bit of a missing link. So this is a little ordinary clock that you probably just have on a table, but it's actually been put into a long case. So this has got weights hanging underneath it. And this is probably the first type of long case clock. Why were they encased? Why were the weights left hanging? It's probably because they were knocked all the time, or your 2-year-old child kept pulling on them in the same way as they poked the numbers on the video set. But they soon developed into these fabulous long case clocks. So there's one with a beautiful walnut case, marquetry, and even more marquetry there. And these are all less than 1700. They're very old clocks. You thought Huygens, the chap from the Low Countries, was good, but this chap is better, and he's English. This is Thomas Tompion. Born in Hertfordshire, he was a blacksmith. His family were blacksmiths, but he was very bright, keen on science, and a very keen mathematician, and very quickly developed an interest in clocks and moved to London to make his fame and fortune, which indeed he did. And he had a shop just off Fleet Street, very similar, I think, to the one we've seen before, but was very much in with the top scientists of the time, and with nobility and with royalty. Let's look at some of his clocks. And this is, again, the typical sort of table or bracket clock at the time, but I think that looks exquisite in its proportions. Again, ebony veneered. The movement there looking really complicated. Remember, this is made without much in the way of machinery. And it's interesting that Tompion, in about a 30-year career, only produced about 600 clocks and produced about 6,000 watches. Very small output. This is probably his masterpiece. So this is the clock without its case, and this was commissioned by William III, and it's a clock, spring-driven, that runs for 1 year. Okay, that's almost unheard of in those days. And moreover, it's also what's called got grand sonnery striking, which means it strikes the quarters, and every quarter it strikes the hour again as well. And for those of you with quick minds, you will have worked out that that's over 59,000 strikes of the bell in 1 year. And that's all delivered for one term of the spring. And here it is in its case, beautifully mounted with all sorts of ormolu ornaments in the British Museum. Absolutely stunning. This is another famous clock of his called the Tulip Tompion. Again, the dial getting more sophisticated and even more opulent as one of a series of 4 clocks he made with lots and lots of ormolu, but also with tortoiseshell veneer as well. In fact, one of these was discovered in a castle in Germany a couple of years ago and sold at Sotheby's for just about £1 million. In my view, worth every penny. Let's look at some of his long cases. This is one of Tompkins just ordinary long cases. Very pretty dial, very standard, very simple movement, very accurately engineered, and that was the key thing. And then these are the Royal Commissions, which are clocks which last again for a year, very heavy weights. But they have another thing on them. They also measure what's called the equation of time. Let's say a little bit more about that. Clocks were now becoming much more accurate than sundials. And what is now obvious from sundials is that the length of the day does vary throughout the year, what's called the solar day. And that's a manifestation of the elliptical course that the Earth takes around the Sun. So there are some times when the Earth is running slow and sometimes when it's running fast. And that clearly differs from what the clock measures, which is called mean time. This was very tricky for people to take on board, that there was a machine now that was actually more accurate at telling time, presumably, than the Sun itself, or rather the Earth, not so much the Sun. Other makers, clocks, again, similar sort of style, different types of wood veneers, again, red-coloured, tortoiseshell there. Chinoiserie coming in the middle of the 18th century. This is a clock by a manufacturer called Windmills, again, exquisitely done. And we've already said that you can't tell time easily during the night, and certainly what you don't want is a clock ticking loudly at night. So this is one which ticks very softly, but actually has a light which lights up the hours, and there's a little light behind a rotating disc. And you've got the quarters there on the arch, so this is actually coming up to 12:30. Another step forward. The length of the pendulum, as we said, determines the rate at which it swings. The length of that pendulum depends on all sorts of things. And if it's a metal rod, it's going to depend on how hot it is. So in hot weather, the pendulum rod expanded and the clock went slower because it ticks slower when the rod is longer. So George Graham had a clever idea. He put a glass jar at the bottom end which had got mercury in it. So as the metal rod expanded down, so the mercury expanded upwards. Actually, there was no change in the overall length, gravitational length of the pendulum. A little bit about watches. Watches began to be made in about 1500. Again, only in our hand. And these were worn around the neck. You mustn't call them pocket watches until getting on for 1600, because pockets hadn't been invented by then. Interesting. But these were exquisite. Look at that most exquisite enamel work again on this beautiful watch. Huygens again, he invented something else. The balance spring. The balance wheel, as we said, rotated fairly inaccurately. But what he did was to put onto it a spring. So as the balance wheel turns, it tightens the spring. And that gives the spring energy to untighten itself. And this greatly adds to the accuracy of oscillation of the spring. He'd also, by this time, discovered the rings of Saturn. That's not bad, is it? 3 inventions in a lifetime. Here it is, you can't see it incorporated into a later clock. There you can see the movement with its little verge crown wheel. And again, the most exquisite casework on the clock, that watch there. Again, this has got a minute hand now. Now, this is an interesting chap. Does anyone know who this is?
Yes.
Yes, this is John Harrison. So he and his brother, born in a little village just south of the Humber, contributed enormously to clockmaking, but most enormously of all to navigation. We'll say more about that. So, he was a carpenter, and he got interested in clocks in about 1720. So here we are, a clock made out of wood. Well, you'd think that was a bit Mickey Mouse, wouldn't you? But in fact, these were highly accurate clocks, and wood is easy to work with. And there's another big advantage to it. Here are the wheels. These are the original teeth on the wheels, 300 years old, hardly any wear. You didn't have to use lubrication for wooden clocks because there's enough oil and resin in the wood to provide that. Mechanical metal clocks you have to. The problem was that they weren't decent oils. They were animal or vegetable in those days, and that used to gum up. And it wasn't until you had mineral oils when you had better lubrication. So, this is another thing they invented apart from wooden clocks. And this is a special sort of escapement called the grasshopper. You can see here it looks like the grasshopper, but again it's friction-free. There's no rubbing of parts on each other. So let's see how it works. Isn't that the most exquisite thing again? Flopping on and off, British Museum. Highly accurate. So it's a slight form of anchor escapement with the difference. Now, we're getting on to knowing where you are in the world. And interesting thought by a Greek chap about how you might determine where you are in the world. And he knew that the world was somehow turning round, or things were turning round around it. What he thought was, if you could see the same event from different places in the world at the same time, somehow you must be able to tell your positions. Okay, he hadn't exactly explained how you could do that. But the event that he chose was actually a lunar eclipse. And you can see this from anywhere on Earth. So that was a first, a very fundamental thought, lost. Until Ptolemy, in about 150 BC, had another thought. That was that you can locate and define the position of anything in the world by two coordinates. At right angles, and we know those now as latitude and longitude, but he also said that these coordinates should be measured in degrees. Also a very fundamental thought. Now, Christopher Columbus. So we're now well into voyages of discovery, and these were people punting off with their boats around the world with absolutely no idea where they were going to go. That takes a bit of courage, doesn't it? In particular, they didn't have much idea about where they were going to navigate to. You could measure your latitude fairly easily by knowing the height of the sun at a particular time, or a star or moon at the night. What you couldn't determine was the longitude. And they did this with rather inaccurate maps, depth soundings, keeping close to the coast. They used an instrument called an astrolabe, very pretty, probably only good at telling you where latitude was. Science, you've been expecting this. So latitude, we've said, is easy. Longitude. So the world's divided up into 360 degrees, isn't it, a circle. 1 degree is 66 miles of the Earth's crust. Or interestingly, more importantly, it takes the Earth 4 minutes to move 1 degree. If you therefore know the time in Greenwich and can keep that time with you and know what the local time is in New York, you can measure exactly how many miles you've gone from London to New York, because you know the time and you know that 4 minutes is X degrees and that equals X miles. So that was the challenge. Is how can you somehow measure the movement of time? Lots of methods. This was one of them, what's called the lunar distance. And it works, there's no doubt about that, but it is highly complicated. So if you can measure with an instrument here called a cross staff, the distance between the moon and the star and their height above the horizon, you're home and dry with longitude. And you can detect that with tables months or years in advance. But again, if you can do this on a boat on your voyage of discovery, you've again got to have a cloudless sky and you've got to have flat water. You can't do this with bobbing about. And actually making these tables and making them accurate was very difficult. The French had an observatory in 1650. That's really irritating, isn't it? And that spurred the English on to also have an observatory. So this is one that was built nationally in Greenwich. Charles II sponsored it. Completed in 1676. And that's what it looked like with a long telescope and various quadrants to measure angles. And in 2001, goodness me, it doesn't look any different. Such is progress. What is important to see is that there are 3 clocks in it. And these are highly accurate clocks in their time, the most accurate in the world, made by Thomas Tompion. They had pendulums which were 13 feet long, and that strikes 2 seconds, and the pendulums are actually above the clocks. So, the combination of being able to observe the stars and time movements is essential for astronomy. And this is a view from the hill of Greenwich, just outside the observatory, down over Greenwich Hospital towards Canary Wharf now. Interesting, isn't it? I think that's rather pretty, actually. I wonder what Christopher Wren would have made of it. I think he'd have loved it, actually. Now, Parliament, being distressed that there were lots of ships going on the rocks, sailors lost, treasury and foreign lands not being discovered and brought home, decided they must act. So they devised an Act of Parliament called the Longitude Act in 1714 to offer a prize for someone who could measure longitude and find it. And the prize offered was £20,000 or up to that if you could measure the longitude within half a degree or 30 miles. That was a challenge. And the Harrisons took this up. Lots of other people did. So John Harrison produced this enormous clock, still at Greenwich today, and this is called H1. This is 1735. It took some time to make, as you can imagine, and it weighed 98 pounds. No pendulum. You can't take a pendulum on a boat, can you? That's not going to work. It was trialled on boats going out to the Caribbean, but pretty accurate, but not good enough. Certainly nowhere near winning the prize. So, 4 years later, H2. Bit better, weighed less. So back to the drawing board. 20 years later, H3, which by the time he got it on a little boat bobbing about in the Thames, he decided it wasn't good enough. So 2 years later, he produced a watch. Nothing big, nothing fancy, an ordinary watch. And this is H4. And the trick in this is actually with the balance wheel, which he made big with a very strong spring. And that makes the balance oscillation very much more accurate. And this was tested on boats again and found to be highly accurate. You were probably well within your half minute. And it was then copied and then became clearly some way of being able to transport your time on a boat across the ocean and measure local time, and you could then work out the longitude. You also needed a sextant, and that helped. They were invented in about 1720. And this is the ultimate development of what's called a ship's chronometer. And interestingly, these weren't adopted by the English Navy till the early 1800s. And they're still used on boats today. Other clocks, development, lots of this. This is by Ellicott, another famous maker. Typical Georgian restraint. And the long case is changed at all. Walnut to mahogany, lots of different varieties, ending up with a classic early 19th century one. And they were much more popular to have musical clocks. So this is one which has actually got a little organ on it again, and little organ pipes. I make no apologies for showing a slightly long clip of probably the greatest automaton clock ever made. And this was made in 1770 by James Cox, London clockmaker, and is now in the Hermitage. It was made for the Tsars. It has actually got a little tiny clock on it, which I'm not going to show, because most of the pleasure of it is actually in all this work here. So, lots of bells doing. This could get on the nerves, wouldn't it? But the Hermitage is a very big place. Very lifelike rotation of owl's head. This clock probably took about 10 years to make. intricate feathers. And then we're going to, at the moment you can see a peacock. And look what it's doing with its tail feathers. So this is all mechanical, wheels, rods. Not available in John Lewis's at the moment. Not quite finished yet. Now it's a little Russian song. There it is. So you've got that every hour, 24 hours a day, 365 days a year. Back to the pendulum. This is another Harrison invention, which is again temperature compensation. It's called a gridiron, and you've got rods of different metals, some push up, some push down, and that equalises out the change in temperature length. Now the French did that somewhat more prettily, I think you'll agree. And these are stunningly nice looking pendulums for long case clocks. Again, all gridiron. And maybe we should think a little bit about the French, because they weren't bad at clocks and they didn't half make them pretty. So these are complicated clocks, all with gridiron pendulums. Apart from this one here at the end, which has also got temperature compensation delivered in a rather different way. And we ought to say something about Abraham Breguet, the father of French clockmaking, who invented a lot of things and made some stunning clocks. And these are two of his what are called table regulators, extraordinarily accurate clocks for their time. And this late 18th century is actually a pocket watch. It looks like something you can get in the shop today, doesn't it? Extraordinarily accurate. This is a French maker called Hartmann, and this is a clock that was made for Napoleon Bonaparte. Very, very complicated. You can tell here almost anything you want to know about time, the sun, the moon, the stars. The French were also very keen on things called skeleton clocks. And here you can see all the movement and the fascination of seeing wheels move. They also invented the carriage clock, arguably a bit dull, but you can move it around very easily, but not always dull, if that is to your fancy. They invented also very elegant but simple clocks, and this is one where the movement is just mounted on glass so you can see through it. So, novelty clocks. So the French in particular were keen on clocks that did funny things. And this is again a clock of mine at home, whereby it appears to rotate and move without any obvious impulse to it. So there's the whole thing rotated around a pivot in her hand. Rather nice bronze lady. Julie Dean posed for this. Ticking away. Okay, so how does that happen? Very clever, isn't it? And I'll show you how it happens in the next video clip as we pan back up. So this is with the back taken off, and you can see the movement. The movement, of course, is rocking. And if we look at the bottom of it, you can see the pendulum. The pendulum actually stays vertical. And it's a clock that actually moves the wheel on the pendulum. And again, the pendulum just gives the clock itself a little move each time, which swings the whole clock. Clever. Absolutely hopeless timekeeper. Pushing it a bit further, everyone was interested still in astronomy, and this is a fabulous French clock made by a Parisian clockmaker called Raingo, which has got on the top of it a lovely little solar system in part of it. The English were keen on skeleton clocks as well, and this is an utterly fabulous silhouette of a skeleton clock, I think, made by a chap called Conliffe in Liverpool, but I think a more relaxing and exquisite design I could not wish to see. And this is what the clock actually looks like. And in its base, it's actually got a music box. Other little novelties. Everyone now, having mastered how to measure time, was looking at novelties and novel ways of trying to make it more attractive to the consumer. So look at this from Escapement. All that little jittery, flippy wheels there. This was made by a chap called Fennell in Brighton, very ordinary clockmaker. Another thing, this is called a rolling ball clock, and this is an oscillator, Escaped, invented by a chap called William Congreve, who was a general in the British Army, interestingly, clearly taking time off from doing ill things around the empire. And here the thing that measures the time is the tilt of this table. Now watch very closely as that ball gets to the end, because this here will flip half the dial and it will move 30 seconds, bang, in one go. And then the ball gets to the other end, so it flips again. So this is an oscillator every 30 seconds. Okay. If you thought the other thing was a bad timekeeper, that is even worse. Austria were doing fabulous things, and Austrian clocks I'm fond of because my dad was Austrian. And these are what are called Viennese regulators. And these were developed in about the early 1820s. Very stylised but absolutely fabulously looking clocks. And you can see here that you've got one with one weight, that means it lasts for a whole year. This is the Grand Solerie, so it's got 3 bits to strike, another pretty one there. Mahogany. This is my own little Austrian clock, which is a pretty little musical clock. Striking 3, please note. There you are. We don't carry that on very often at home. Now, how's that operating list going? I'd nearly forgotten about that. And there is Mrs. Dean with the operating list indicating that we've got to speed up, otherwise we're going to overrun the list. It's 12 on our electric clock, but we've got up till 5:30, so no big sweat there. Now, this is an interesting chap. Edmund Denison, later Lord Brimthorpe. He was known to be very, very crusty in his time, and I think that's reflected in his stunning photograph. How does he feature in clockmaking? Because he was the chap whose design was accepted for the great clock in the Houses of Parliament. And the clock was made in conjunction with a firm of clockmakers called Dent. The bell is the thing that's called Big Ben, not the clock, but you all knew that, of course. And in fact, the first bell was made in Stockton-on-Tees, 14 tons, brought down on ship, tested in the clock yard with an enormous hammer, and after about 5 strikes it cracked. That was the end of that bell. So much for the north of England, which I suspect has never recovered. Mark Scriven, who's married to Sharon, is a northerner. So another one had to be made in trusty London, in Whitechapel. And this was less than 14 tons, but still had to be transported by 16 horses. And it was winched up, put in place. And there was then a big debate in the House of Parliament to decide what this bell should be called. Bells at this stage always have names. The bell in St Paul's is called Old Tom. The commissioner for the works in the Houses of Parliament in general was a chap called Benjamin Hall. And in the debate he stood up and talked at length about different names, whereupon a backbencher stood up and said, for Christ's sake, why don't you shut up? Let's just call it Big Ben. And that's how it stuck. And here's the movement, a very short clip of this. But it's a massive thing. It's 15 feet long. There you are. No bells, fortunately. So, it's crashed again, I'm going to. Sorry. There we go. Now, another fact. We all know about adding pennies onto the weight, don't we? they have some significance, and they do alter the timekeeping. If you put a penny on the weight, will the clock gain or will it lose? Mumbling, I hear some lose, there's a bit of gaining over there.
It's on the weight, it's not the pendulum.
Okay, the weight itself doesn't matter. It actually gains because you've actually shortened the functional length of that pendulum. And 1 penny is equal to 0.2 of a second per day. Get that? Okay, now, we're not far off a really big breakthrough, and that's the use of electricity in clocks. So Alexander Bain, who was a Scotsman, of course, they've got to contribute to our society, and he invented electric clocks. So here we've got at the bottom a pendulum which has an electromagnet which operates over, a coil that operates over a magnet, and it's regulated by regular impulses. And this has 2 immediate impacts. The first is it's very much more accurate as an oscillator. The second is to then transmit that signal to any other clock you fancy. And this came at a time when telegraph was developing around the country. And here is the clock installed by Charles Shepherd in Greenwich, which was the timekeeper for the entire United Kingdom for about 50 years. Electric clock, and you can see 2 of its what are called slave clocks alongside it. But this was telegraphed around the whole country. And this was called Greenwich Mean Time. Now, I know you can't see much of this map, but there are some red circles. Interestingly, these are places which still kept local time. They kept their own time. And of course they are actually behind Greenwich because they are further out in the world. But of course it's a nonsense having bits of the country telling different times. May I say that Oxford and Cambridge were 2 of them. In 1847, though, this was all put to an end by the railways. It was clearly impossible to run railway timetables with all sorts of different time. Further refinement with pendulums and electricity. Sigmund Riefler in Munich did a lot of work on pendulums, and he particularly looked at barometric compensation. So again, the barometric pressure influences the swing. Also available at this time was a metal alloy called invariable, which was iron and nickel, which actually had no coefficient of expansion at all for temperature. So these were very accurate clocks. Moreover, he also decided that you can put the clock in a vacuum. If you do that, there's no friction from the air, and barometric pressure simply doesn't matter. Communicating time a bit more. We've heard about the telegraph around the country, but here we've got transatlantic cable, successfully laid in 1858. Interestingly, the year before they started out to lay one, and after 1,000 miles it broke, and that was that, back to the beginning again. That's life, isn't it? So they laid one in 1858, and then they went back, found the old one, spliced onto it and did it again. So you've got 2 of them. So this now connected us to America. Look at this interesting group of onlookers here. So we wonder what all the people are doing in our operating theatres, looking at us while we're operating. But actually nothing has changed, has it? So this is America. We're now connected to America. Charles Dowd had also an interesting but blindingly obvious thought, and that is that America is 3,000 miles wide, and that actually the time differs from east coast to west. And actually you can't have everyone getting up to work at the same time, because it's light somewhere and dark somewhere else. So he invented time zones. And in fact, time zones which he recommended are the ones pretty well unchanged from today. And then, of course, the whole world adopted this scheme. Has America contributed anything to timekeeping? The answer is yes. They went into huge mass production of clocks and pretty well shafted the European clock manufacturing industry. On a positive side, though, this is a musical, a burlesque musical called Grandfather's Clock, and that is how grandfather clocks got their name. Thank you, America. Back to Greenwich. This is the Greenwich Meridian. So this is 0 degrees. The whole world begins here if you want it. And in the middle there is a telescope which they used to look at stars at and watch them cross this meridian. Now, how is this important? Well, there were lots of different, what people call prime meridians. The French had one going through Paris. There were lots of meridians. There were lots of different longitude systems. There were lots of different ways of making time. There was a big conference in 1883 where it was decided actually everyone would use Greenwich Mean Time, and this was the prime meridian. Everyone took a vote, and everyone voted in favour, apart from the French, who abstained. Because actually, 80% of the world's boats used Greenwich Mean Time, and actually 70% of the world's tonnage of boats also used Greenwich Mean Time. This was then slightly changed to being called Universal Time. There we are. There was actually an interesting little twist to this. The French in the end said, oh, OK, we'll use it, provided you British go onto the metric system. OK, so big smile and filed in rubbish bin. Now, electric clocks developed and became quite accurate, and this is an interesting clock, which was the timekeeper for the BBC. Again, this is in Upton. Noisy, doesn't look very pretty, triumph of mechanism over art. This is the clock with all its slaves, there's one slave above it, that was in front of, say, the newsreader on the radio. Here we are, made by a famous company called Synchronode. And here is something you'll be familiar with. Do you know what this is? This is the speaking clock, yes. So there's all these little wheels and discs. And there it is connected to a clock which is a pendulum swinging all on its own, interestingly, with a little impulse. So there's no friction on that pendulum from anything else. All its vibrations recorded electronically. I put Einstein in here because he was around about this sort of time. And as we know, he slightly invented time, although I gather our neutrino experiment in Westwood may undermine this. Quartz clocks invented in 1928. So this is again an oscillator. If you put an electric current on a quartz crystal, it vibrates at about 32 cycles per second, and you can translate that into something electronically. The accuracy of these clocks was immediately about 2 milliseconds a day. They're now even more accurate than that. The first commercially available domestic one was this Amiga clock, which was from the early 70s, interestingly. And you'll all be familiar. If you had a Bulova Accutron at school, no one. Ah, Tennant, well done, ahead of the times. The class creep at my school had one. But we sorted it out in the lunch hour. Vive Mickey Mouse. All of this was superseded by the invention of the cesium clock in 1949. This is a British invention, interestingly. And this is again all about movement of atoms. And the cesium atom vibrates at 9 billion times a second. Don't ask me how that's translated into a clock, but it is somehow. So, this is accurate to 1 second in 1,000 years. In fact, the latest atomic clocks are accurate to 1 second in 10 billion years. Is that any use? Actually, it is. What I would like to say is, isn't that pretty? Would you have that in your lounge? I personally wouldn't, but it doesn't tick. And this has all been in a way superseded and congealed into GPS. So in order to have really, really accurate understanding of where you are in the world, you have got to have absolutely accurate time. And you can't have a space project and satellites without having accurate time. And this is the one that was taken by Robin Knox Johnson on his round-the-world trip. What it is now telling us is that the technology is very, very much more accurate than Earth as a timekeeper. So forget the Earth altogether. I'm going to tell you, though, that art still lives. Look at these exquisite watches by Breguet again. Skeleton ones, anything you care to mention. And look at this here. This is one made by an American company, a skeletonized wristwatch, but listen to this. Not finished yet. Grand sonnery on a detective. Another little dinger. So these you can buy for about $1.5 million. Wristwatch with as many hands on it as you care to mention. Extremely accurate. And this is another very pretty little thing. This is what's called a tourbillon. This was invented by Breguet, who observed that the escapement slightly alters its accuracy according to the way it's tilted. So he invented something that tilted itself. And here it is implanted into a wristwatch. Now, isn't that the sort of thing that you could spend all day watching? Maybe not. And it's the sort of modern equivalent of the French, would you like to come home and see my cousin? Okay. And then, final little clip. This is of a clock that was made for the centenary at the Horological Institute. So this was designed locally. It's basically an electric clock. And this is again something you could probably watch each day. So you've got the dial above it, seconds at the top, different bits of the world if you want. And what is intriguing with it, as we paddle down, is that it's got more than one pendulum. It's actually got 3 of them, all beating together. Okay, so there's 3 separate escapements, all beating in succession. And here comes the second time ticking round at the top. Brilliant thing. Not currently available. Now we're in dead trouble, because while I've been daydreaming, watching my little Oris wristwatch, we've overrun the operating list. It is now 10 to 6 and I'm in trouble. And Mrs. Dean gets angry if you overrun your list, because all the staff have to hang on. So Julie, I'm sorry. As a result of this, though, we're going to make some improvements in timekeeping in the urology department. Now, I may just say that during my training in Nottingham in the urology department, I received mixed messages about timekeeping from the consultants I've worked with. There was Patrick Bates and there was Mike Bishop. One of them kept clock time very accurately, the other didn't. I'm not going to say who was who. But what we are going to institute is our video monitors outside the department, which here is reading 10 to 6. That's going to be installed by Boopies very soon. And that is that. I finished. Thank you very much for listening.